So we have one more week after this, and we will be moving into chapter 12. I may finish this today, chapter 11. Chapter 12 is coming up. There's actually a lot in chapter 12, and I'm not going to try to rush it. So whatever we get done, we get done. But we may not finish all of chapter 12. I think there's a lot of information in there to try to cram all into 1 week. So we'll see how that goes. So somewhere we'll end probably 2/3 of the way through chapter 12 or something like that is my guess. But who knows? Maybe we'll just fly through it all on one day or something. Question?
For the 342 classes coming up this summer,
Yes.
are they going to really continue?
So yeah, that's a good point. If you're going to continue 342, it will start in chapter 13. So if you miss a little bit at the end of chapter 12 and you're going on to 342, you may want to read through that and brush up. And I know you guys all have the tools now to learn on your own, right? You don't need me. I can set you free with an organic book. What more can you ask for? Okay, so yeah, that's a good point. So there might be a little bit that you missed. We'll see. Maybe I can get it all done. Okay, aromaticity. So remember we talked about this on Wednesday, that molecules which we refer to as aromatic molecules, or arenes, have these ring structures in them with full conjugation. And we're going to talk a lot more details about the properties of these and what makes this aromatic stability. There's lots of names for these. I don't know that I'm going to really be asking much in terms of names for these, because I don't want to focus on that. I really want to focus on the chemistry and not have you memorize all these names. But if you continue on and you are using these things in your future work, you really should be familiar with some of these common names. Remember these, when we talk about the structure of benzene, it is a 6-membered ring with conjugation completely around the ring. So there's three pi bonds if we write one of the resonance forms. But in fact, all of the electrons are delocalized throughout the whole system. And so it really is a single pi system where all 6 electrons, there's 6 electrons in the pi bonds that are all essentially circulating around. They could be found anywhere within that system. And we see that when we calculate the electron density maps or the molecular orbitals. This is the lowest energy occupied molecular orbital, which you can see here, describing that pi system. And notice the plane of the ring in that lowest energy orbital has one sign for the orbitals all on one side of the ring and the other sign for the orbital on the other side of the ring. And if we look at those molecular orbitals, this is what gives rise to some of the special stability we see. When we have fully conjugated systems that happen to be tied in a ring, and then there's continued conjugation throughout, what happens is the molecular orbital energies start to become degenerate. What that means is we see more than one orbital at a specific energy, and that ends up overall lowering the energy rather than having them stacked. I have another picture a little bit later comparing hexatriene with cyclohexatriene or benzene. But what you notice here is that if we look at these energy levels and the 6 molecular orbitals, symmetry means 2 of these are at the same energy as opposed to one being higher. And all the 6 electrons are in this region of bonding orbitals when we fill it. So it's just like electron configuration filling, really. We have 6 pi electrons. It starts at the lowest energy orbital and then you fill up. Just like you would do for electron configuration for an atom, right? 1s2, 2s2, 2p6, etc. Those all increase in energy. It's the same concept, really, but on the whole molecule, just looking and focusing on the pi bonds. Okay, and that extra stability that's gained by this conjugation in a ring is demonstrated here if we see the hydrogenation and the heat released when we reduce it all the way down to cyclohexane. That what we would predict theoretically just based on the energy of a double bond, if there are 3 double bonds, we would expect 360 kilojoules per mole of energy release. But in fact, we only get 208 kilojoules of energy released. And that's because the molecule is at a lower energy to begin with. It's more stable, a lot more stable than a simple alkene or a triene. And that leads to some differences in reactivity. And so I want to focus on reactivity properties of these systems a little more today. I mentioned before that to take those pi bonds in a benzene ring and reduce it to a cyclohexane requires a lot of energy to do it because there's an activation energy barrier and the molecule is pretty stable. So you have to generally use very strong conditions, harsh conditions, and very, very active metal catalysts. So under typical conditions, reduction is one of the ways in which we can deal with the chemistry of arenes, but it's forcing conditions, I would say, difficult to do because of the great stability of this. But you can see high pressure, high temperature, we can get that job done. But not necessarily the most convenient way to do it if you have other functional groups in the molecule and you just want to reduce this. There is another reaction. Some of the main chemistry of arenes is what we call electrophilic aromatic substitution. So it's not the typical reaction of an electrophile like Br2, which we think about as adding a Br+, right? You know the chemistry very well of Br2 reacting with double bonds. It doesn't do the same thing, or we don't end up with that same result when we react with benzene. But a different reaction takes place. And we're going to talk about the similarities and the differences in those, and that's the focus of chapter 12, is mostly this particular reaction. But instead of adding to the double bond and getting a dibromo compound, it essentially takes a position on the ring, one of the hydrogens, and replaces it for a bromine. It's a substitution reaction. Now, not with a nucleophile, but with an electrophile. Bromine is a Br+. Okay? The other thing that the benzene ring provides is stability for other reactive species, whether it's lacking electrons, like a carbocation intermediate, or a free radical intermediate, or even if you have other double bonds conjugated, that benzene ring affects. Now, this benzene ring is conjugated even with that double bond. So if you recall, when we talked about dienes, and we talked about the reaction of, let's say, a diene with some electrophile, like in this case Br2, you had this on the quiz on Wednesday, right? You could get reaction like that, or you could get reaction like that, and that was the answer on the quiz, this one. Because we form carbocations which are in resonance. And so another thing is if you take this with HCl, right, we would get this more stable carbocation as opposed to another carbocation. This more, we see that more in a ring. Well, that's the same thing for a double bond next to a benzene ring. You're always going to form the carbocation adjacent to the benzene ring to generate these kinds of stable intermediates. So if I were to add HCl to this, right, and protonate it, okay, that would be the intermediate, and that's because that double bond now can undergo resonance. It can be spread out all the way throughout the ring. And we'll be dealing a lot with these kinds of resin structures of putting plus charges throughout this ring as intermediates in the next chapter. But what it does do, this benzene ring activates the position next to it for a lot of different chemistry that we can't do with typical alkanes or even alkenes. So there's some things that provide us a handle of reactivity that we can take advantage of. This is a reaction, actually, which is similar to the reduction of triple bond that we had before. Remember, we could reduce an alkyne to an alkene in the trans orientation with a reducing metal. This goes by electron transfer. So this is a similar kind of reaction, referred to as a Birch Reduction, named after the person who discovered this reaction. And you'll notice something similar here to the reaction we had before. So remember, if we had something like this, and we reacted this with sodium and in ammonia, right? What's the product? The trans double bond. It's reduced from a triple bond to a double bond. Besides hydrogenation, which is very, very difficult on benzene rings, reactive reducing metals like sodium can also react with them and reduce one of the double bonds. And it's a very useful reaction synthetically because it seems to be quite selective in a lot of ways. And so remember, this sodium atom has an electron in the atomic state, right? And it goes by single electron transfer. It actually takes 2 sodium atoms to do this reaction overall. But notice what happened. We have now removed one of the pi bonds. We now only have 2 left, and we have 2 sp3 carbons present. So overall, we've added one equivalent of H2 to this, right? But how does that work? Well, it's quite similar to the reduction of an alkyne. What happens is that the electron on the sodium is just transferred to the benzene ring, and if I flow these electrons here and these electrons here, I can draw this particular structure where we have a carbanion, we have a free radical. Notice we start with 6 pi electrons, we add an electron, there's a total of 7 electrons in that system now. Okay? So always keep track of your electrons. If I transfer an electron from the sodium to the ring, we have to have overall 7 electrons, right? The best resonance form for this, and you can think about drawing resonance forms, putting the negative charge in different places, or putting that free radical, that lone electron in different places. But the best, the most stable resonance form is the one I've drawn, putting this free electron and the lone pair as far apart as possible. Okay? So that's why it goes selectively to give the 2 double bonds no longer next to each other in the product. So from here, this is very reactive intermediate. And so in this case, you have ammonia or even methanol. That's a source for a proton. Okay? So that would give us a protonated form. I'm going to draw the other one. Notice on the benzene ring at every position that's not substituted, there's a hydrogen. So that carbon is now an sp3 carbon. Okay? Here we have a free radical. So you can see how we get one of these hydrogens on there. Methanol protonates that carbanion, which is very reactive. It's an acid-base reaction. Okay, and as soon as that's formed, we need another equivalent of sodium with 1 electron. And what that does is it takes this very reactive free radical and adds the electron to it to make another carbanion. So the intermediate would be this. Okay. So notice a lone pair again with a negative charge, and guess what happens? You add a proton to it, methanol. That grabs the proton. Okay, so that's overall 2 electrons and 2 protons are added to the benzene ring. Okay, I've taken some time to go through the mechanism just to reorient you again with thinking about electrons and where they go. You don't necessarily have to remember this mechanism for an exam or anything, but knowing how reactions work helps you understand the chemistry. This reduction, Birch Reduction, just want to point out some features of that. As I said, because of the presence of these reactive intermediates, free radical and negative charge, that provides the positions that are as far apart as possible to give the 2 double bonds that are on opposite sides of the ring in the product. So you can imagine if this reaction were carried out, why couldn't you get isomers like this, where it's these, right? that's typically not formed in this kind of reaction. Because that would require an intermediate which might look like that. And having those reactive groups closer to each other is not as stable. This would be a resonance form. Oh, I erased it, sorry. This would be a resonance form of the other one I drew here. Push these electrons down here and push these electrons there, right? It's a valid resonance form, but in fact, most of the electron density is on the end, okay, and radical. So we have good control over that. The other aspect of that is if you have groups which are alkyl groups, they end up on the double bond, not on the sp3 carbon. And that's because alkyl groups are electron donating, right? Electron donating. Think about how that connects to everything you know now. If you have a carbocation, what makes it more stable? More alkyl groups around it. Electron donating to the carbocation. This is different. If we have a carbanion, if you have a carbanion and then you have an alkyl group on it, that's less stable. Because you have an electron donating, which is trying to donate to something that already has a lot of electrons. So that decreases its stability, raises its energy. That's why you get selective positions as well. So electron donating groups always end up on the double bond. What would you think would happen if instead of R being alkyl, R was an electron withdrawing group? What if R was electron withdrawing?
More stable.
The intermediate, which would put the carbanion here, let me just change it from R to, I'll just say electron withdrawing group. Okay, if you put the carbanion there, that's more stable now. Let's say we have this intermediate as a stable resonance form. That's stabilizing. Putting the negative charge somewhere else would be less stable because now if we're withdrawing electrons, we're helping to spread out charge. So you see how donating groups and withdrawing groups affect the charges and the stabilities of the various resonance structures that we draw, putting negative charge around the ring. So actually, the nature of that group depends a lot. I think your book focuses mostly on alkyl groups. But the principle is it stabilizes or destabilizes depending on the property of that group attached. That changes the positions of the double bonds and the negative charges in the intermediates.
Would that one make a different product then? With the electron?
Yeah, so what would happen here is, I'm not going to draw every intermediate, but what would happen here is the proton, a proton would go in this position, and then an electron would go here again, and the proton would go there. The product would be electron withdrawing group. Notice the positions of the double bonds. So the substituent is on the sp3 carbon. That's the difference. Okay? Okay, let's look at some other chemistry. Oxidation chemistry. We haven't talked a lot about oxidation reactions other than we've done ozonolysis of various functional groups. We've done making epoxides with metachloropurbenzoic acid on alkenes. Those reagents don't do much with benzene rings. Benzene rings are very stable. As a matter of fact, alkanes are very stable. It's hard to do any reaction with alkanes, right? They're all sp3 hybridized, CH and CC bonds. They're not easy to break. And so if you use some kind of strong oxidant, in this case, sodium dichromate, it's a very strong oxidant. Chromium is in the 2, 4, 6, 8, let's see, 1, 2, 3, 4, 5, 6, in the +6 oxidation state. That tends to oxidize the heck out of lots of different functionality. But notice, alkane. You treat that with a very strong oxidizing agent like dichromate. There's no reaction at all. and nor would you really expect much. If you react benzene with sodium dichromate, heat it up under acidic conditions, it's a very strong oxidizing conditions, no reaction. Okay? Alkenes would be just destroyed with these oxidants, but benzene is too stable. Okay, but notice what happens if we make a benzene ring with an alkyl group on it. And we treat that with sodium dichromate and heat it up under acidic conditions. It does oxidation of the side chain, not of the benzene ring, of the side chain. The product is benzoic acid. Benzoic acid. Okay, notice the carbon next to the benzene ring was oxidized. It had all CC and CH bonds before, now it has 3 CO bonds. Oxidized as far as it can go and still be attached to the benzene ring. And this reaction is somewhat unusual because what happened is it actually broke a carbon-carbon sigma bond. Not just a double bond. Remember, ozone could cleave a double bond, but ozone doesn't react with alkane. Chromate doesn't react with alkane, as shown in the top reaction. Doesn't react with benzene, but it reacts with an alkane when it's next to benzene. And it doesn't matter what else is out here. It will break everything off, leaving one carbon next to the benzene ring, and then oxidize that up to the carboxylic acid. Okay, so why would it do that? What's so special about the benzene ring that allows that to happen? Well, the fact that benzene ring stabilizes carbocations, free radicals, all of that means that this benzene ring and the conjugation of it is also weakening CH bonds and even CC bonds. So it's more prone to, granted, chromate is a very strong oxidant, but it's more prone, it's much more reactive to break those bonds. Easier to break those bonds than it is just an isolated alkane. And that's fortunate because we can take any kind of benzene ring substituted with alkyl groups and oxidize them up to benzoic acid. You could take something like, let's see, do I group it right here? What if I took this molecule? Benzene ring fused with another 6-membered ring. Those are 4 alkane carbons attaching that. And I use the same reaction conditions. What happens? 2 carboxylic acids, that's right. Not only does it break the one here, I'll highlight in blue, there are 2 carbons, alkane carbons, adjacent to the benzene ring. It cleaves that bond and that bond and oxidizes both of those positions. So what you get from this is a dicarboxylic acid. So you get that and that. Okay. So it can be a very useful reaction sometimes to break things apart. And what it does now is give us more functionality here. And if you, in 342, you'll learn a lot about carboxylic acid chemistry. Okay, so it's a very useful reaction synthetically. Well, I want to come back to this stability of benzene because I talked about the fact that aromatic rings like benzene are more stable because they are fully conjugated. That means there's a p orbital on each atom, each of the carbons in the ring, and it's tied in a ring. So notice 135 hexatriene, that's not in a ring. If you calculate the molecular orbitals, there are 6 molecular orbitals for the pi bonds because there are 6 p orbitals we start with that the mathematics is combining together. And they would be sequentially up in energy. Bonding orbitals, 6 electrons, anti-bonding orbitals. Compared with the benzene that we saw before, 6 molecular orbitals, but they are degenerate in 2 of those. Okay? So what's important for aromatic stability? conjugation throughout the whole ring, and the fact that it's a ring. Okay, but there's more to that. And if you take a look at these examples, let's look at some different size ring molecules. Okay, butadiene, cyclobutadiene. Here's cyclobutadiene. It satisfies those requirements. It's got 4 carbons. It's got a p orbital on every carbon. So you would think it should be the same thing, right? But in fact, cyclobutadiene is a very, very reactive molecule. It doesn't exist at room temperature. Only at very, very cold temperatures could you have it. As a matter of fact, this molecule, if you have this at room temperature, it will immediately dimerize through a reaction you know. What kind of reaction do you think that would do? What do you think that would do? It's a Diels-Alder reaction, that's right. Diels-Alder reaction. So we take one double bond of one of them with the diene of the other. They're the 2 ends of the diene. Okay, if I push those electrons there, push those there, and then those here to form a bond, what do we get? A dimer. And that would look like that. Now that doesn't look that good either. It is a strained molecule, but this is a heck of a lot more stable than cyclobutadiene. Notice it's not conjugated anymore. Okay, why would it give up that conjugation? Why doesn't it want to be next to each other? As a matter of fact, if you look at the structure of cyclobutadiene and you look at the bond lengths, what you see is actually there is a difference now. There are single bonds, which are 1.56 angstroms long, and there are double bonds, which are shorter at 1.35 angstrom long. Remember, benzene, all the bonds are equal. That means there's full conjugation. What that tells us is that cyclobutadiene, the p orbitals, these are like 2 isolated double bonds. They're not necessarily conjugated. So why doesn't it want to be conjugated? Good question, huh? Same thing we see with cyclooctatetraene. Now we have 4 double bonds in an 8-membered ring. And if it were also had this aromatic stability, it would be flat. All the p orbitals would be aligned, and then we'd have that full conjugation. But in fact, this molecule is puckered. It's not a flat molecule. It means that this p orbital is not aligned with that p orbital. Oops, sorry. Drawing terrible. So it's not benefiting from conjugation and stability of being aromatic. Okay. So what is different about these than about benzene?
Not completely conjugated?
They are completely conjugated. They would be completely conjugated if they were flat and there was full communication. Okay? But there is a p orbital on every carbon, so in principle it should be. So it's not the conjugation, it's not the ring. If you look at benzene, it has 6 electrons in the pi bonds, right? 6 pi electrons. How many pi electrons are in this one? How many electrons in pi bonds? 4. There's 2 double bonds, so there's 4 electrons. How about cyclooctatetraene? 2, 4, 6, 8. Okay. If I had a system that was 10 electrons, 2, 4, 6, 8, 10. That's 5 double bonds. That's aromatic and stable. Interesting, huh? If I have a molecule which looks like, let's see, what's another molecule that has only 2 electrons but fully conjugated in a ring? If I take cyclohexene, propene, and let's just take the carbocation. That's a 3-membered ring. Since it's an odd number of carbons, I have to have something else to have a p orbital, right? So there's a p orbital on every carbon, and a plus charge overall on this molecule. This is stable and aromatic. It has 2 electrons. Okay, I don't know if you see a pattern here, but what happens is that in order for aromatic stability to exist, there has to be a certain number of electrons. So the properties needed to have aromatic stabilization is not just having a flat ring that's fully conjugated, but it has to have a certain number of electrons. And the formula, general formula, n being any integer, if n is 0, 4n plus 2 would be 2 electrons. Cyclopropene carbocation has 2 electrons. If n is 1, right? If n is 1, 4 times 1 is 4 plus 2 is 6 electrons. That's benzene. If n is 2, that's 8 plus 2, that's 10 electrons. That's the 5 double bonds in a row. Okay? But 4 electrons or 8 electrons, you can't put an integer into this simple formula and have that come out. Okay? So this is what's referred to as Hückel's rule. Hückel is the one who studied this aromatic stability. And then you should be asking yourself, well, what's so magic about this number of electrons? Why is that important that we have that number of electrons? Okay? It has to do with the fact that in a ring that's conjugated, right, if I go back to the molecular orbitals, benzene has degenerate orbitals. If there's not enough orbitals to fill them all, or not enough electrons to fill them all, you would predict it would be an unpaired state. So let's take a look at this. Here's benzene, here's cyclobutadiene, and cyclooctatriene. So we have 6 pi electrons in benzene. You've seen this energy description of the molecular orbitals. 6 electrons fill, 2 here, and then 1, 1, 1, 1. So all of those bonding orbitals are filled with pairs of electrons. Okay? If I look at cyclobutadiene, we start with 4 p orbitals in that 4-membered ring, right? Combined mathematically, that would make 4 molecular orbitals, with 2 of them being degenerate in energy. Okay, so just like you would do electron configuration and filling 1s2, 2s2, the 2p orbitals, you would put 1 at a time until you fill them up, right? When you're doing atomic configurations, it's the same principle. We have 4 electrons. We start with the lowest energy orbital. We put 1 electron in, then we put the second electron in. Then we have to go up to the next energy orbital. We put 1 electron into that one. There's another one at the same energy, so we put the second electron in that one. And we're out of electrons in the pi bonds, right? There's only 4. So if this were in this configuration, it would predict there would be 2 unpaired electrons. And that's not good, right? That's unstable. Actually, to avoid that, it doesn't conjugate, so it can avoid that. It actually does separate these energies and pairs them up, but it makes for very reactive orbitals. We actually refer to these situations as molecules which are anti-aromatic. They're actually more reactive than you would predict. Anti-aromatic, because that would be a very high energy state. Okay, so unless you have the right number of electrons, here's the 8 electrons, and now we have 1, 2, 3, 4, 5, 6, 7, 8, a total of 8 molecular orbitals. Again, you start with 1 lowest, and then you have degenerate orbitals, degenerate orbitals, degenerate orbitals, and then 1 at the top. That's the 8 orbitals, and I just covered it all up. And if you fill that with 8 electrons, again, you end up with a situation where you have unpaired electrons, if it were in that state. So it doesn't want to do that. It'd rather not be conjugated. It would pucker, it puckers that ring so that the double bonds aren't communicating with each other. Then they no longer have this symmetry. They no longer have to unpair to be in this state. Okay, does that make sense? And if you remember on Wednesday, when I first introduced these energy pictures for molecular orbitals for benzene, remember I said that if you draw the ring with a point on the bottom here, and the energy diagram kind of looks like the ring? Okay, it's a good mnemonic to be able to remember this. Here's 4 carbons. We start one on the bottom, 1, 2, 3, 4. Okay, and here's 8. 1, 2, 3, 4, 5, 6, 7, 8. Not the best ring, but you get the idea that you could actually mnemonically assemble a picture of the energies of those and predict that based on the number of electrons. I don't want you to get too lost and confused in that. What I want you to remember, and probably the easiest thing to remember about this in determining what's aromatic and what's not, is remembering that you need this number of electrons to avoid those situations. That's what's important about that formula for numbers of electrons in the pi bonds. If you have 4n plus 2 electrons, all the electrons are always paired in bonding orbitals. If you don't have that number of electrons, you have a situation where it would have to be unpaired, or higher energy. Question?
What is it?
N is just any integer. So if you just start with 0, 1, 2, 3,
Okay, so it doesn't actually pertain to
it's not, it doesn't mean anything, it's just an integer. So if you have 2, 6, 10, what would be 3 that's first row? 14, right? Yeah, and so on. That's the magic number of electrons for aromatic. If it's not those, it's not aromatic. Okay, actually I forgot to put this slide in the handout. I uploaded a new handout with this, but it's just one page. I want to talk a little bit about ions. So remember I talked about cyclopropene carbocation, right? Cyclopropene is down here on the bottom. And if you take a look at cyclopropene, without being charged, it has one double bond in it and an sp3 carbon. Okay. On the other hand, if you have cyclopropene, where you have a plus charge, a carbocation, now you have a 3-membered ring with a p orbital on every carbon. Overall, 2 electrons and 1 plus charge. So this molecule overall has a plus charge. Okay. It's a flat, fully conjugated ring. It just has an odd number of carbons, so it has to have a charge. Something has to be missing in order to have the p orbital. And it has the right number of electrons. If n is 0, that would be the right number of electrons. That's an aromatic molecule. It's pretty stable. Now, it's not as stable as a completely neutral molecule, but it's much more stable than a carbocation. Okay? What if I had the other situation? What if I had cyclopropene carbanion? Is that aromatic? Well, you could envision this, right? You could envision this where you have the pi bond here and then 2 more electrons, okay, which could be delocalized, just like we have negative charges on oxygen delocalizing through resonance. You could imagine that, but why wouldn't this be stable? There's 2 electrons here and 2 electrons here. Okay, overall 4 electrons. That doesn't fit with the Hückel rule, 4n plus 2. Right? That's an anti-aromatic situation. 4 electrons, just like we saw with butadiene, cyclobutadiene, not stable. So with a cyclopropene, one of the charged species, if you lost something from it, is aromatic, the other is not. Okay, and it depends on the total number of electrons again. So if you look at cyclopentadiene, how would you explain the fact that an alkane or even an allylic CH, if you wanted to deprotonate it with a base, has a pKa of, I don't know, 30. Cyclopentadiene, those hydrogens are quite acidic. pKa of 16. This is as acidic as water. How do you explain that? You can take that and react it with sodium hydroxide, you form a significant amount of cyclopentadiene anion. Okay, why would it do that? Well, look at it. Look at this ring. If I draw this anion, what have we just created? A situation where we have now two double bonds and a fifth carbon that has a lone pair of electrons. Overall 6 electrons. Okay, and now it could all be conjugated together in a ring. The anion of cyclopentadiene is aromatic. The cation would only have 4 electrons, right? So that would not be good. Cycloheptatriene. This is not conjugated because it has an sp3 carbon, but if you remove something from that carbon, what do you have to leave behind? A plus charge or a minus charge to be aromatic? We start with 3 double bonds. Okay, that's 2, 4, 6 electrons. So if we left the electrons behind and made a carbanion, it'd be 8 electrons. If we took the electrons away from that carbon and left a carbocation, it'd be 6 electrons. Which one's aromatic?
6.
6. That's good. You got it. 6 electrons. So in this case, cycloheptatriene is aromatic. It's fully conjugated once you now have an empty orbital. And it needs to be empty because there's already 6 electrons in the double bonds. You see how that's working? So you could envision all kinds of different ring systems, which has that magic 4n plus 2 number of pi electrons where all the atoms are conjugated together. Sometimes you have the right number of electrons, and you have a ring system, but for other reasons, it can't be conjugated. Let's say for steric reasons. So if we look at this molecule on the left, C10H10, we have 1, 2, 3, 4, 5 double bonds. So there's 10 pi electrons, right? And 4n plus 2, if n is 2, that should be aromatic. But this molecule isn't planar. Why is it not that planar? It physically can't have all the atoms in one plane. If you draw in the hydrogens, you'll see why. Because there's a hydrogen here, okay? And on that double bond, I'll draw it. I'm exaggerating the bond length, but you get the idea. That hydrogen is there. Those double bonds, which are pointing towards each other in that ring, they can't be in the same plane. It can't be flat. It has to twist something like that to avoid those hydrogens bumping into each other. Okay, so it's just because of steric reasons. It's forced out of plane. If the double bonds are forced out of plane from each other, they can't be delocalized. Okay, so you don't gain that stability from delocalization. Notice this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 18 electrons. That's aromatic. And this molecule now is big enough. If you look at the hydrogens, I've highlighted here the hydrogens which are pointing inwards. As you know, there's hydrogens pointing out as well around this ring. But this is far enough apart now that they don't bump into each other. That's very stable, and aromatic has the right number of electrons. It can be planar. So there's lots of different molecules with various ring sizes. If they're flat, fully conjugated, and 4n plus 2, they get that extra stability. And they don't all have to be carbons. So here are some examples of aromatic rings which have a fully conjugated system, but involve other atoms besides carbon. In this case, usually nitrogen or oxygen. It could be sulfur. There's even some molecules which are aromatic with phosphorus in it. Here are some good examples, and it's important to recognize and know which electrons on these heteroatoms, like nitrogen and oxygen, which of the electrons are involved in the conjugated ring system and need to be aromatic, and which are not. So if you notice here, this molecule on the left, we've seen it before as a mild base. This is a molecule called pyridine. Okay. Notice it has the same structure, or similar structure as benzene. Okay. The difference is, instead of a CH on the bottom, we have a nitrogen. Now, since nitrogen is trivalent, there's just no hydrogen on it. Okay? But what you'll notice is that there is a double bond between carbon and nitrogen. So if you look at the p orbitals on every atom, and here's a side view of that, it looks something like this. So notice if we have a double bond, if I were to draw one resonance form, a double bond here, double bond here, double bond here, that double bond means that nitrogen is sp2 hybridized. Notice this lone pair, it has to be 90 degrees apart. Okay? So the two electrons on the end of pyridine aren't in the same plane to be conjugated with the other double bonds. So it's an aromatic molecule because we have 2, 4, 6 pi electrons in a ring, fully conjugated. That other double bond is not involved. Or that other lone pair is not involved. Which means that lone pair is available to, say, react with a proton. You could put react with an acid, you put a proton on there. This is available for reactions. Okay, acid-base chemistry. Compare that with this molecule next to it, which is called pyrrole. Pyrrole. Now we have a molecule with 5 atoms. One of them happens to be nitrogen. And it has 2 double bonds. So there's 2 electrons there, 2 electrons there. That wouldn't be aromatic. This nitrogen has a hydrogen on it. It's the hydrogen that sticks out. This is like cyclopentadiene anion, except instead of a carbon, there's a nitrogen. Okay, so that lone pair of nitrogen, if you put that in conjugation, makes that stable and makes that aromatic. But it also means that that lone pair is not stuck there on nitrogen. This is delocalized and less available for reactions. Okay, so it is important to recognize which lone pairs are available and which are in resonance for the aromatic ring. And I think I'm going to stop there now. I will touch again on this on Monday, and then we'll probably move into the next chapter, chapter 12.
So pyrrole is not aromatic.
Pyrrole is aromatic, yes, but you have to include the lone pair of nitrogen to be aromatic.